Hello community! Today we're gonna look at some snowflakes up in the Nordic, in the Arctic region. And we look at a 128 times 3 billion mixture of expert system. Now you can alter the size here, like for example 22 billion or 3 billion free trainable parameter. And this is interesting, but I have never seen a 128 expert system. And you know where I learned about this? Reading the Financial Times. Unbelievable. So here we have a brand new 480 billion LLM, and you know me, when I find something interesting I shared with you. Here you have my YouTube channel here, the community tab, where yesterday I provided you with the first information and said, what an interesting architecture, more details soon. And now is soon. Now we have mixture of expert system like the 22B mixtral system. And let's see here what NVIDIA, the developer blog, tells us about this. And they say, hey, it has advanced capabilities. Understand and generate complex text. This model is suitable for more complex tasks that require a deeper understanding of language. And it's a 22 billion free trainable parameter model. So the size matters. And you see my last video where I told you here about from Microsoft this new PHI-3 MINI with just 3.8 billion, a tiny little LLM to run locally on your phone. And now let's run with this idea of a simplification. Let's say, okay, imagine we build an expert system with 9 times this little 3.6 billion LLM, and this is symbolized that it runs here on each single phone. You say, maybe I need 16 expert system here that run here on these little phones. Or maybe I need 22. What is the right size? And the company decided here for our clients it is 128 experts and a size of 3.6 billion free trainable parameter plus a 10 billion dense transformer. Now, a lot of you ask me, how do you do your background search? How do you validate your understanding? Well, beautiful here to show you. New with OpenAI, now in April 2024, they have improved some tools, and now with file search I can upload more than 10,000 files for an assistant. So I uploaded all the PDF files from archive about mixture of expert system. And yes, I had to pay OpenAI, but this is the way I do my background research. But of course, if you want to do it, there's also a simple way. You just pay ChatGPT-4, connect to the internet and says, explain what is the benefit of a high number of experts in a mixture of expert system. And GPT comes back and says, indeed, it offers substantial benefits, especially when properly managed. And it says, mixture of expert models can better specialized, allowing for each expert to handle specific types of tasks or data types. This specialization can lead to an improved model performance and efficiencies in resources during inference. It scales dramatically without a proportional increase in computational demands. And this is because this sparsely gated mixture of expert layer activates only a subset of the available expert at any given time, requiring less computation per unit. So you see, we are here in a direction, so with higher experts, it is really more efficient. And here we look at load balancing and the primary challenging of load balancing, if memory and computational overhead, how you do this, how about the complexity and the training and the tuning and the routing mechanism. I will show you here some new research in a second about the fine-tuning stability. So you find a lot of literature. It has its advantages in the efficiency, but it is rather complicated to implement. So there was a lot of research to be done by this company to build exactly this mixture of expert system. And I would like to show you a little bit of this research here. And you have here from GitHub, Snowflake, the labs, the Arctic model here. To identify the bottleneck, uses here the deep speed profiler to identify the teraflops efficiency and latency issues. Real interesting is the custom fused kernels, implementation of a rogue fusion, and then the activation checkpointing, the reduction of the communication overheads, and there was a lot of new methodologies to develop particular for this LLM. And therefore, I thought it is fascinating to see here the pros and the cons. But of course, I ask myself, why are they doing this? 128 experts. Is this necessary? And then I found this here on the official documentation, as you can see here, Data Cloud Arctic. And here you have it. On the x-axis, you have the compute used for the training, so the amount of computation. This means also the cost. And on the y-axis, you have the enterprise intelligence. And it took a little bit of time, and I found that enterprise intelligence equals to the average of the SQL generation, the coding, and the instruction following benchmark data. If you average all this data, then you get here a certain accuracy over a combined accumulated enterprise intelligence. Beautiful. Now we know this. So now let's have a look. For example, the Llama 3 70B, we know this is here far outside. But on the same, if you want percentage accuracy, we have also Snowflake Arctic. So another model that tells us, hey, I achieve your accuracy and your performance, but look at the compute that I use to achieve here the same result, compared that you need, 16 times more compute resources. So it is about cost, and it is about scaling, and it is about efficiency. And now you get exactly where we are going here, and thanks to Snowflake's AI research for this result. Now, if we do the inference run, you see here, again, enterprise intelligence, but now we have the best performance to cost ratio is now the important thing in this blue triangle. And you see again here far outside the Llama 3 70B. And then in this triangle we have here the Mixtral 8x7B, we have the Mixtral 8x22B. And as you can see here by the official documentation, it has a higher performance or a better performance than Arctic. But if you have on the x-axis your active parameters, you see this model is here relatively smaller to this model because although it has in total 480 billion, they are just 17 billion operational. So this is an interesting approach I've seen for the first time. Absolute focus on performance to cost ratio. So we are not only just in the research where we say, give me the best performance independent of the cost, but now they do here the measure of performance to cost. An interesting way to see it. Now for the architecture, they have here some beautiful overview. I want to show this. So if you have a dense transformer like a Llama 3, you know this. If you have the classical mixture of expert transformer like the Databricks RX or the Mixtral, you are familiar with this. And they went with a hybrid transformer architecture from a dense and a mixture of expert system. And now, of course, was the question, hey, what about the gating mechanism? This is interesting. So what they did, they have here the 10 billion dense transformer model with a residual 128 expert system, each 3.66 billion free trainable parameters, resulting in 482 billion total, but operational are only 17 billion active with a top 2 gating mechanism. So we have 2 experts operational. So for my green grasshoppers, what is a gating mechanism in a mixture of expert architecture? It is crucial. It's managing how the inputs are directed to the different experts within the model. And in this new Arctic model, we have here a top K gating. Simple, it determines which of the 128 experts, each expert being a specialized part of the model, should receive a given input based on their thematic relevance to the specific input. It selects the top 2 experts for its input. Then you have the dispatch mechanism here. So each expert processes its assigned token. You have then the output collection. And in total, you have an optimization of the gating mechanism that brings overall efficiency to the mixture of expert architecture. So if you compare now a dense transformer with a mixture of expert, you see here that a mixture of expert allows here for a quality improvement without proportionally increasing the compute cost. So you see, we keep our efficiency, our costs down. So this decouples here the total model size of 480 billion from the computation, 17 billion during training and inference, leading to a more efficient scaling. Now, at least I try to understand here what is the difference between those two systems. So you see, it is all about efficiency. It is that you have a fixed training cost set, and then you try to get out the best efficiency, and you're looking for each and every efficiency gain structure. Or you want to reduce the inference cost, and you found that here a mixture of expert model with 1.6 billion active parameter and a 6.5 billion parameter dense transformer model showed that a mixture of expert system achieved a lower loss and requires 4 times less compute to train. This means it is significantly cheaper. Now we understand here it is all about efficiency. But of course it is also about performance. And they say excelling at enterprise metrics like code generation and SQL requires a vastly different data curriculum than training models for generic metrics. And they say that over hundreds of small-scale ablations, we learned that generic skills like common sense reasoning can be learned in the beginning, while more complex metrics like coding, math, and SQL can be learned effectively towards the later part of the training. Now, okay, so let's look at the first element. Let's look at first at reasoning, and then later videos we'll look at code generation and SQL. Reasoning. You know I have reasoning test, and we will do this here with a progressive complexity increase. But at first, let's see here what's good about this. We have an Apache 2 license, which is a real open source license, not like Llama, where you have a particular license. This means this is great. A particular detail, Arctic here, our 480 billion LLM, has a 4K attention context window, and they are working to extend this to a 30 key context attention window in the near future. Okay? And now Snowflakes give us here their performance data. And you see here, in the first column, Snowflake Arctic, our 480 billion total, with 17 billion operational LLM, plus here Llama 3 8B, Llama 3 70B, and our Mixtral 8 times 22B. And I just want to focus here on one model and make it a simplification of the official training data by Snowflake. Have a look at this. So here we have with Snowflake a 128 times 3.6, and here we have just an 8 times, but now a big 22B system. Let's look at the result, at the performance. In SQL, it seems to be on equal footing. In coding, it seems that Mixtral has a better performance. In instruction following, which is important, it seems that Mixtral, according to Snowflake, has a better performance. In mathematics, it seems that Mixtral has a better performance. In common sense and an augmentation and an average of 11 metrics, it seems that Mixtral has a better performance. And in general world knowledge, it seems, according to Snowflake, that Mixtral has a better performance. Seeing this, I was a little bit, I said, but why? I mean, it's great that they are so transparent that they show us, look, these are the performance data for this model and these are the performance data for our model. And then I understood that the whole presentation was about cost efficiency, which in my mind, if you build a 480 billion LLM to talk about cost efficiency, but they managed to build here a mixture of expert system that is really cost efficient. And now, of course, you have here the big question, performance versus cost. from the performance standpoint, just looking at the official data by Snowflake, you see that a different system has visibly a better performance. So it is about cost and cost structure. But me focusing here on the research aspect and on the technology develop aspects, I will focus more on the performance of the system. And here Snowflake has something beautiful. They have here a cookbook, and here I want to show you the second entry here, and they explain to you how they did the pre-training of this system. And this is highly recommended for you to read this, because they have detailed documentation about their parallelization strategies, how many thousand GPUs they used, how they can here use their custom fused kernels here, techniques like group fusion and addressing here the bottlenecks. And this is a highly interesting technical annex if you're interested to pre-train your new LLM on a cluster of GPUs. However, if I'm focusing here, if the performance of a system is better, if I have a small system with a lot of experts, or I have just some experts with much bigger system size of our LLM or free trainable parameters, I have some pros and cons I thought about, but whatever. What's really important is here the real world benchmark test. So I have here an ice cold question. How is the performance of the system in real world application? So let's have a look at the results. To evaluate the reasoning capabilities, I follow here the Stanford test routine I showed you in this particular video about logical layers. I used the same Stanford routine for Databricks RX testing. I tested Llama 370B Instruct on the same dataset and the new Microsoft PHI-3 3.8B LLM. And now we go here to Snowflake Arctic. You see, I go here with a conservative temperature. My top P is 0.9. This is perfect. I cleared the chat history, so I think we're good to go. I start here with a logic reasoning text. And here we go. This is fast. Yeah, perfect. Goes through. Conclusion. Yes. And this is wrong, because if rus then rif is not equivalent to if ris then rus. Okay, next one. Here we go now with another logical test from Stanford. Beautiful. Snowflake Arctic goes off and says, okay, so we go. There are two conflicting conclusions, no more rules, so this is the wrong answer. Okay. Third test. We have now a simpler, a more textual-based simple test, also from Stanford. And you know the result is 24%, and we get here 62% chance. This is the wrong answer. Now, let's simplify here this a little bit and run the same test again. And you know the result is 24, but unfortunately we still get 62%. But positive is it is identical to the test before, so some modification in the test does not alter it. And I say, can you validate your answer? And it goes off and says, yeah, validation is running, okay. So there's a 56% chance, which matches the initial answer of 62%, and this is wrong. Next example. Okay, we go here with a logic test, also from Stanford. We have rules defined, we have facts defined, and a simple query. And the result is the answer is true, because this is the explanation. Now, this explanation does not make sense. And I ask the system, explain this step by step and show me all the rules and facts that you apply. And it just copies and gives me the identical answer. So I say, write out the logical argumentation step by step, and it just gives me the same answer. So it's not following my commands. So I say, what do you mean here with app assumption? And they say, which means we are temporarily accepting it as true for the sake of the argument. And this is not something you should use here in an AI argumentation, that you say, hey, temporarily, I think this is true for the sake of the argument. And I told him, hey, I've given you a definite set. Stick to the rules. Follow here my instruction without any assumption from your side. And I get the same response again. And I said, is your assumption in the rules? And it says, no. So I'll re-evaluate the argumentation. And the argumentation are now re-evaluated, and I get an answer that has nothing to do with my original question. So I say here, okay, this is my query. Is Alice Pope? I put this again in, and I ask here again, please, this is here the task, the query I've given to you. Please answer here. So you see here, this is my original query was rules. Here are the rules, then 2 facts and my query. Is Alice Pope? And answer this. Now the answer is false, and this is false. It's a failure. Next example. Okay, we follow Stanford another time. 2 facts. Is Alice Joan? Is here the question. Comes back and says the answer is false. And this is the wrong answer. Next example. Now I have here that I say, okay, maybe I have to give him instruction how to solve this. So I can say, hey, list all the facts, apply all the rules, keep a record, systematically explore all the ways, document your pathways, continue till no rules are unexamined. And then I give it again here the logical task. So I have here an absolute clear path to follow to solve this question in context learning perfection. And this is not a result, and the result is the last one, the answer is false. And this is the wrong answer. The system failed another time. So now I think, okay, I say, let's go here with the textual. And I give him here a textual exercise. I say, solve this task. We are on Mars, and on Mars we have a problem. We have a paradox of quantum entangled AI decision-making in a closed ecosystem on Mars. We have a scenario 1. We have chain A and a chain B. So decide A or B in a scenario 2. And we have a solution C and a solution D. We have hypothetical outcomes. I tell you what it is. And now the question for the AI, causal reasoning. And the result that I get back is just a summarization, but not that it understands that it has to solve the task given. It just summarizes that these are the tasks. So the system fails this test again.